Hello everybody. So in this chapter 11.3, we're going to talk about inertia tensor. It's going to be a pretty long chapter, so I'm going to divide it in two videos. So the chapter starts by saying that we have a rigid body composed of n particles of mass m alpha, with alpha going from 1 all the way to n, because we have n number of particles, and it rotates with angular velocity about a coordinate system that is going to be this coordinate system over here. And this coordinate system is moving with velocity, capital V, based on a fixed coordinate system that I drew here. So this one is the fixed one, and this one is the moving one. By one, I mean coordinate system. So what is the kinetic energy of our object? Well, first of all, let's think about it. Inside our coordinate system, the moving coordinate system, the kinetic energy will be equals to 1 over 2 m and then v squared. Now, since we're talking about a series of particles, we're going to have 1/2 and then the sum of the particles, so m alpha, with alpha going from, sorry, actually, you know what, let me name it, actually no, m alpha is fine for now. Alpha going from 1 to n, and then v of alpha squared. Now v of alpha is, no, let's keep it for v of alpha right now. And since we know we have a rotating system, and the v is equals to w cross r, and it's going to be v alpha is going to be r alpha, we can substitute it inside our equation. We get 1/2 the sum of the particles from 1 to n, mass alpha, and then w cross r alpha squared. Now, as you can see, I'm going a little bit different from what the book is going, and I'll show you why at the end. And then the kinetic energy with respect to the fixed frame will be equals to what? Well, we have t is equals again 1/2 mv squared. We're talking about a series of particles, so we're going to have 1/2, and the sum of these particles, alpha is equals to 1 to n m alpha v alpha squared. And in this case, you know what, let me use these things in blue so they're easier to understand. In this case, our v alpha is equals to capital V. Let me do it bigger, capital V. So we have 1/2, then the sum, alpha is equals to 1 to n of m alpha capital V squared. Now this would be the kinetic energy for the fixed system, and then this one is for the rotating. Well, you know, the moving, not rotating. So if we put it together, the total will be equals to, well, the first one plus the second one, right? I think so far everything's clear. Now I'm gonna do based on how the book solves it. So the book instead takes another approach. It takes the approach of the particle, so our particle, from the fixed system, so from this point right here. So we have different velocity to add. We have the velocity alpha of that particle will be equals to the capital V, because we're a rotating system, plus the V tangential, or Tn, 10. And V tangential we said is equals to what? Well, W cross R. And of course we're going to use um, all the subscripts. That means that our kinetic energy, which is equals to 1/2 m v squared, in our case will be equals to 1/2 m, actually, let me write it in a different way. So T alpha is equals to 1/2 m alpha, and then V alpha squared. So we just substitute it, and we get 1/2 m alpha, and then this part right here squared. And this is for a single point, but we're talking about a series of points. So T total will be equals to 1/2 the sum of our points. So alpha is equals to 1 to n of m alpha times this part over here. So far everything's fine. So now we can expand this part and get 1/2, and then the sum alpha is equals to 1 to n, then m alpha. I said let's expand this part. So the first one squared, so b squared, plus the double product. So we're gonna have 2b times the w cross r alpha plus the w cross r alpha squared. Okay. Yes, sorry. So now we can take one of these results out. Let me just actually, yes, let me take one of the results out. I'm gonna take this result right here out. So this result is equals to 1/2, and then the sum, oops, the sum alpha, and then times 2b, then w cross r alpha. Now these two cancels out with 1/2 outside. Remember, we're only taking one part of the whole entire thing, and you'll see why. So it's equals to the what? Well, the addition of m alpha and then times v times w cross r alpha. But if we look at this a little bit differently, and we take out some constants from here, so for example, v does not depend on alpha, so we can take it out, and then we're gonna have times w, because again does not depend on alpha, cross with the sum of m alpha r alpha. And sorry, from alpha is equals to 1 to n. Forgot the notation, just want to make sure you get it. Okay, so this part over here is equals to what? Well, it's equals to m r. But the center of mass does not move in our case. So we can say that the velocity of this, sorry, the kinetic energy of this is equals to 0. So V, and the cross product with this is equals to 0. So now what we get is the other two parts that we left, so this v squared and this part squared. So we'll get this one right here, copy and paste over here. And now let's go a little bit more down. And then, yes, capital V squared plus the second part right here. There we go. So now, if you notice, we got the same exact thing, okay, that I got previously over here. I can rewrite what I wrote over here so you can see it better. This is equals to what? This is equals to, let's collect everything that is the same, so 1/2 in front, the summation from alpha is equals to 1 to n of m alpha times, well, the first part is this one over here, but we can always write this one over here. It's always a plus in between, so v squared plus our w cross r alpha squared. So in two ways, we derive the same thing. I believe the first one is more of a concept. This one is more of a concept because if you understand it, it's way easier, as you can see. But this one works just as well. If you forget the concept that you want to check it different ways, of course you can do it the long way as well. Okay, so in fact the book then after add that the translational kinetic energy, sorry, not the translation, the translation, so the one that moves straight in a straight line is equals to 1/2, and then the sum m equals to alpha b squared, or we can take out 1/2, take out b squared because it's not based on alpha, and then the sum of m alpha is equals to 1 to n. But this part over here is simply equals to capital M, right? Because it's a total mass, so 1/2 capital M b squared. And then instead the rotational doesn't really change. The rot is equals to 1/2, and then the sum of m alpha is equals to 1 to n, then w cross r alpha. Okay, I believe everything is oh, I forgot squared over here. That's what was wrong. Yes, okay. So one more step that we can do is we could take this part right here, and by using a product rule, that is a cross b squared is equals to a squared b squared minus a dot b squared. So we can rewrite this as 1/2, then the sum alpha is equals to 1 to n of m alpha with a squared b squared minus a dot b squared. Okay, so the rotational energy will be equals to, oh, of course I just rewrote this the same way. I should have actually used a and b, the actual things are. So I'm gonna have w squared r alpha squared minus w dot r alpha squared. There we go. So let's complicate things a little bit, because we do physics, so we like to do things as complicated as we can to include all the generic, to have the most general case we can have. So I'm alpha again, and then we get that if we take, actually that's one step before this, r alpha can be broken down into its many components. In this case, if we use continuous axis, we're gonna have the x, the y, and the z components of alpha, alpha, alpha. Or written in a different way, we can have e alpha 1 comma e of alpha 2 comma e alpha 3. Or like the book does, it uses always x, so x of alpha 1 comma x of alpha 2 comma x of alpha 3. I believe this is a very confusing way, but that's the way the book does it, so we're just gonna go ahead and use it. I believe this wants to be a better way, but we don't get to decide how to write the book, so we're just gonna go ahead and use this. So we can say that w squared is equals to what? Well, it's gonna be equals to, if we break this down in pieces, this part right here, okay, squared minus w dot, then this part over here again, close parentheses, squared. Now let's write it in a little bit easier way. 1/2 summation from alpha is equals to 1 to n of m alpha. And then we're gonna have, we're gonna have the alpha that has to be applied to every single one of these. Therefore, we're gonna have the omega to be applied to every single one of these, w. So we're gonna have the summation of the, summation in terms of I of our omega I squared that multiplies what? Well, we can rewrite this part in a more compact way. So summation of x alpha, let's call it j because we want to do something different. J, okay. And of course squared minus, again, we're gonna have our, in this case the squared is outside the parentheses, so we can just take, it's like taking this and then multiplying by the same thing again. So we can say that again, we're going to take the omega and use the subscript. So in this case, we're going to have I, and then our x in terms of alpha depends on I, yeah, it's great fit now. And then the same thing now for the second time. The second time though, now instead of using I, we're going to use j, j of our omega, j x alpha j. Let me put this on the side a little bit, so it's. I think I'll just have to cancel it. I think you guys got it. So actually, and well, let me do this. Okay, perfect. Okay. However, we know that our omega I, I'm doing both. Omega I is equal to the summation of, oops, there we go. Okay, it's equal to the summation of our omega j, which in our book is missed. For some reason they forgot to write omega, times omega I. And we know that since we're talking about two different coordinates in a dot product, if we multiply these two, we get 0. If we have 1 and 2, if we're multiplying, for example, x alpha 1 times x alpha 2, we get 0. But if we multiply instead x alpha 1 with x alpha 1, we get instead 1. A way to write this is using our chronometer, I believe that's what it's called, delta, so with I, j, so that's what we're going to write down here. So our chronometer delta with I, j, prefer to write the I first. Okay, so we can substitute it. No, sorry, this is not the one, this is I. Okay, so let's rewrite our T, kinetic energy, again, because that's what we're doing. 1/2 of summation of m alpha, and then we're substituting our w for this value right here. Okay, so we're gonna have alpha is equals to 1 to n. I don't want to make any mistake because here is where the stuff begins to be a little harder. Let's move this a little more so we can put all the summation Okay, and then we are gonna have I and J because here we had I and J. Okay. Okay, M alpha, and then one thing I wanna do, even though we could take, let's talk about it later. So we're gonna have our omega I times our omega J chronometric alpha delta I J, and then we take the summation of our x. Sorry. Oh, yes. So I'll talk about it in a second. So x alpha k squared. In this case, here we didn't use the j, the book uses k, just so we have a different uh, denomination. Doesn't really matter for right now. So with k here, k squared again because this part over here was squared, so we didn't touch that part yet. Minus, well, since we can change our w, so our omega, or w, whatever you want to call it, I think it's just easier to say w, to omega I, omega j, and x alpha I, x alpha j. Remember that all this, we're getting rid of these summations in front because we put it in front of everything. So I and j is taken care of there, and we're also taking care of the fact that they also have to be equal to 0 by using this chronometer. I don't remember exactly the name, but that's how we would use it. Okay. So now the book does a little trick, doesn't explain why, but you can see after how it works. So it takes out the I and J, but then it only takes out what is in common between them. So it takes out this part here and this part here. So we do the omega I, omega J, yes, and then the summation alpha. Now, as you can see, we're not actually changing anything. We're just factoring out the omega I, omega J, and then our chronometer, I always forget to say, ij, and then summation again, of course, times of k of x alpha k squared, put it always in parentheses so you don't forget, get confused, minus what's left in the second part, so x alpha I, x alpha j, and then one thing that we can do is say that the moment of inertia, so I, in terms of ij, is equals to the summation of the mass of alpha, summation of the mass alpha times the chronometer delta, sorry, j, and then our summation in terms of k of x alpha k squared minus x alpha I, x alpha j. There we go. So we can substitute it in our equation and we get that t is equals to one half summation of ij wi, sorry, I w I is the other way, sorry, iwj, and then our I, let me do a little bit, ij, and of course these two have to be the same to be equals to 1. So we're going to have 1 half our omega squared times I, which will be ij, but again, if these two are different, then we're gonna have 0, so it's gonna be simply I. And this is the ending, so our rotational kinetic energy is equals to 1/2 omega squared I. It's a long way to get to this point. It's actually helpful for the future, we're gonna see in the next video, but as you can see, we started from a system with 2 reference frames, and we ended up having a very easy rotational, uh, fixed, let me do clear, fixed kinetic energy. I don't know what we call it fixed. The book actually called it translational because we're moving on a straight line. 1/2 capital M B squared, and the rotational there is equal to this, and then we simplify the rotational by making it a little bit harder in the meanwhile in order to get this part here. So theta t, the translational, is equals to 1/2 capital M capital B squared. So we can say that total kinetic energy is equals to 1/2 times our capital M B squared plus omega squared I. As I said, this is pretty easy to know because, of course, this has been proved in the past already, and we know that the kinetic energy for a rotating object is equal to this. We could have added it to the kinetic energy of our translational system, and we found it, but we just proved how to find this part here. I hope this was helpful. I'll see you in the second part of this video.